Okay, so this is what it looks like when you click into JASP. A couple of things to know about JASP. JASP does not, you can't create data files in JASP. So you have to create the data file in another program and then you link it to your JASP. So I often use Excel. That's the easiest, but when you open a file in Excel and create that file, you need to save it as a CSV file for JASP to be able to open it. So just make sure it's a CSV file. If you have old SPS files that are SAV files, SAV, JASP will open those as well. Once you have data in JASP and you have the data file somewhere else, they are linked unless you move one of them, and any changes you make in the Excel will update in the JASP, and we'll see that a little later in one of my demonstrations. All right, so I'm going to click on these three little bars right here on the upper left, and I'm going to go to Preferences. And in Preferences, I'm going to go to Data. And what you need to make sure is checked is this Synchronize Automatically on Data File Save. So you want to make sure that preference is checked in the JASP. And that's the only thing under data. Under results, I like to have exact p-value, normalized notation, and then I set it to 4 decimal points. So those are some preferences for the tables. And then I choose white as my default for what the background of my graphs are. But if I'm going to know I'm going to be putting, say, a table on top of a colored background, say in a PowerPoint, I can also choose transparent, and then it'll show through the color of what's behind it, right? So you have those options for your data as well. For the interface, I don't think there's anything. You can change your themes, you can change the preferred font, all of that is adaptable, but really it's just the data, synchronize, and setting up your results the way you want those. Those are the preferences that I'm usually change. Okay, and you only have to do that once. Once you've done it, it's done. All right, so let's go on through. This is the document. It's got a table of contents. This is what the students see. We'll come back and talk about G-Power in a little bit. I just want to jump on down to page 19. That's where I'm going, 19. And we're going to talk about descriptive statistics. So I have a data file here, which I can actually save, see, copy hyperlink, and I can put it in here for you. It should work. So there's the data file, HW1 lab. And so what we're going to do is use that data set in order to do some descriptive statistics, box plots, and histograms. So I'm going to go into JASP. If you download that file to your computer, it's a SPSS file. So just you download it to your computer, and then you're going to open it from your computer. So I have it all saved in a file called class files. Where's it at? It's right here. So you can see how this shows up because I don't have SPSS on this computer. So the file's here. The computer doesn't know how to open it. That's why it looks kind of like a blank page. But when I click on it and I open it up in JASP, JASP knows what to do. It opens it up very easily. So let's go over a few things with JASP. So now my data file's open. So you have these symbols, much like are in other programs. So I can click here to change from scale, ordinal, or nominal. These are my participant numbers, or the participants, the number of the participants, right? So it's nominal, so that's correct. Age is a scaled variable, so that's correct. Sex is nominal. When I first brought this value in the very first time, they were coded as 1 and 2, right? They were coded as 1 and 2. And so I literally just click on sex, the word sex, and I can make labels. I can change these to be whatever I want them to be, and it will immediately change it. So if I wanted to change this back to, say, a 1, I can also filter by it, so it only highlights the females, or I can highlight and only see the males. So it's very easy to use in that way. Okay, so I can name these anything I want. Same thing with COVID, pre-COVID. These were originally coded as values 1 and 2, and I've recoded them to be pre-COVID and COVID so that when I have tables and charts, I'll be able to see what I'm talking about. The reading score is also scaled because it goes for a range of data. So this is my first data set. And so this is the data view. If you're familiar with SPSS, we had a data and a variable view. So this is the data view. Now I want to do something with this data. I'm going to go ahead and close this, which is that top part. And now I can see my data, and I'm just going to go to descriptives, just going to click right here, and boom, it pulls up the descriptives. All right, let's say that I want descriptives of age. So I move the age over, but I want to know about age across the genders, right? And so what I did there is, if I take this back out, whoops, go back out, there's nothing. It just has age in general. So it's all of the participants, and it's the mean, maximum, and all of that. But if I want to split it out by gender, boom, it automatically does it. One of the things that I really like about JASP is it's instantaneous, right? I'm seeing my results as I'm telling it what to do. It's popping up over here. So that helps me know, is that what I wanted? Is that not what I wanted, right? It just is immediately there. Now I can come down here and there's more options. I can click statistics. Let's say I want to have more statistics. I want mode, median. Maybe I want to check skewness and kurtosis. I want the range, variance. I can click anything, and you can see it's filling it in as I go. So it's immediate. All right. And then for basic plots, I can do a distribution plot. I can tell it if I want density or what's called rug marks. But this gives me the male breakdown and the female breakdown. I can also do QQ plots to see if there's any type of linear relationships in my variables and how they're fitting along the best fit. I can also do scatter plots and box plots. So box plots, I have a lot of great options. I like to mark outliers. So it'll label the outliers. So what it's doing is, there they are. There's my box plots. So here's the box plot for males. Here's the box plot for females. These, of course, represent the quartiles. So this is, the top quartile, next quartile, quartile, and next quartile. And then it's labeled my outliers. I have 2 outliers for the female, clearly labeled. So I know participant 12 and participant 7 are considered outliers. And then I'd have to make a decision, of course, as a researcher as to what I wanted to do, if I was going to keep them or not, and why. And then I can also do scatter plots. I like to do linear here for the regression line, so it shows an actual line. And where did it put it? It must be trying to put it somewhere. Where are you putting it? Scatter plots. Sometimes they take a little while, but I don't know why it's not coming up. We'll come back to scatter plots because I'm not sure what's going on with that. Oh, I know why. We need to have 2 scores. There we go. So we had to have something to correlate it with. So the reading score correlated with the age, and now that's a scatter plot. That scatter plot is showing density. So if I want a cleaner look, I can just take these out so it's not showing this density. And this is the confidence interval. So it's demonstrating how confident I am that these scores fall within, the population statistic or parameters. So I can unclick that, and then I just have a straight up scatter plot. Okay, any questions about the descriptives? It's pretty straightforward. But okay, thanks. All right, so now a couple of things about JASP. Let's say I want to go back to my data. I can just click this little arrow right here and boom, I'm back to data. I want to go back to my results, boom, hide data. If I want to make this bigger, I can do that. Okay, so I can kind of scroll through these. Now, if I want to take this chart and put it in, say, a paper, I just click right here and hit copy. And then I can actually show you, it comes up very nicely. And I can just do paste. Boom, there it is. The other advantage of JASP is it is in APA format. So the tables that come in are already formatted in APA format. So you don't really have to do anything new with them unless you want to spread them out or sort them out a little bit. But it's already in APA 7th edition format. So that's another big advantage for the students. Same thing with the charts. Anything you can see, you can copy. You can also do of course, like snipping. You could do the snipping feature, right, where you have the snipping tool, which is in your apps, and you can just hit new, and then you can snip it. But I like to copy it because if there are changes, I like to do it like this, because then if there are changes, I can manipulate it. Like if I copy it like this, right here, and I put it in my chart, which you'll see here in my Word document, I can actually take out rows or add rows if I need to. So now I can manipulate it. So that's the advantage of copying it versus snipping it. All right, I can't think of anything else. Let's say that I didn't like this descriptives and I wanted to start over. I could just get rid of it and start over, right? I can also do other things with it. So let's say that I wanted to run a correlation, which we'll talk about a little bit, but this is regression, and here's a correlation. And so you see the descriptive statistics is still up here. I can just open that back up, close it. Same thing with correlation. If I want to correlate age with the reading score, is going to not give it. Why did it? Oh, I know why. Got to put them both in the variables. There we go. So now we have a correlation matrix. So age, of course, is not going to have anything because that's 1. Reading to reading is going to be a 1, but this is the correlation between the age and the reading score, which is not significant. So that is interesting. Okay. And with this correlation, I can also do Spearman-Rowe, Kendall. I can do, if I had a one-way or a single, like one-tailed test, I could choose whether I thought it was positively or negatively. So do scatter plots here as well. So it's just an example. We'll come back and do an example of this, but I just wanted to show you how to toggle through all of these. Okay. So that is an example of the first thing. So let me go to another data set to show you how to create, because sometimes when we're using descriptive statistics, we might have a lot of information, but we want to kind of pull that information into domains or into subgroups or subscales. So I want to show you how to do that. So I'm going to open up a different file. Go, and I'm going to open up, and I'll give you guys a copy of this in a second. It's which one? Let's do CPCE 2021-22. Let's see if I can give you guys a copy of that file so you can play. Actually, I'm going to give you a link to the whole data sets that I have for the class. And that way you'll have the whole thing. You just download this folder and then all of them will be in there. So I'm going to put that link in here. So you want to download this folder. It'll give you all the data files that I'll be playing with today. All right, so in this particular data set, you can see that I have a set of CPCE scores. So I have human growth and development, social cultural, helping relations, group work, career development, appraisal, research, program evaluation, and professional orientation and ethics. There's the student's total score. You can see gender is coded 2 and 1, and ethnicity is coded 1 through 3, I think. Okay, I'm going to bring up my document because I got to remember how. I'm going to bring that over here so I can remember who's coded as what. Okay, so first things first, I'm going to check my level of measurement because that's super important. In order for JASP to run the data correctly, it needs to know what the level of measurement is. So I know that all of these right here from the CPCE domains should be scaled. So I'm just going to click on this and change these to scaled so that it is looking at the correct level of measurement, because it won't do certain things if the wrong level of measurement is selected. Okay, so I also see that gender is coded 1 and 2, and that could be really confusing if I try to do a, say, let's do total score, and then I'm going to split it by gender. Well, I don't know what that 1 and 2 means, right? So I don't know who this is. So I need to code my data so that I know what this gender means. So I'm going to click on the word gender. And for 1, it should be female. Let me my notes, female. And 2 should be male. And you can see it changed female automatically. As soon as I hit enter, female corrected on the data set. And male, I hit enter, and it corrects on the gender. So now I know what that 1 and 2 means. So that is a helpful cleanup. All right. So now this is a lot of data. And I know that for the CPCE, some things kind of group together. So I'd like to create subscales so that I can interpret this data a little bit differently instead of looking at each individual domain. So I'm going to create subscales. So I'm going to click this little plus mark here. I'll close this one actually and open this one. So I'm going to hit plus and it's going to say create a computed column. I'm going to call it subscale A. So, and unlike SPSS, I can actually have spaces in the name. So you can do subscale space A. It's going to be a scaled variable, and I'm going to hit create column. And it's going to bring up this computed column, subscale A. I'd like to create a subscale that represents kind of the techniques classes, the how to do counseling classes. So I'm going to put human growth and development. I just clicked here and I hit plus. I'm going to do helping relations, group work, and career development. And I'm going to say compute column right here. And boom. What it's done is it's added up those columns that I told it to create a new subscale score. I'm going to do the same thing again, and I'm going to do subscale B, create column. And this one, I'm going to do assessment and research because, you know, that's students' favorite ones. Now, you may notice right here that when this popped up, I don't have my little compute column screen here and that I can't see it, right? And when I scroll down, I can't see it. Sometimes this happens with JASP, especially if you're using an external monitor. So all I have to do is just do this. So I just minimized and bring it back up and then it shows it to me. So that's just a little glitch that sometimes happens, especially with external monitors. And then I hit compute and I have my next one. Okay, one more. We're going to do subscale C, which is going to be professional orientation and social cultural. So again, social cultural plus professional orientation. Again, my compute is gone, so I'm going to click this and then it reappears for me. And now I have 3 subscales, subscale A, subscale B, and subscale C. And this just means the function X just means that it was created using the compute column. So it's not part of the original data. Any questions about how to create subscales? Because that happens a lot. Like if a student uses the DAS, for example, the disability anxiety stress scale, they would want to create a depression score, an anxiety score, and a stress score. You know, there's lots of ways in dissertation work, especially that students might need to combine scores to represent something, and this is the best way to do that. Okay, anything? All right, I'm going to close this out. So I'll click this little X button. I see you typing, Tiffany. So, all right. So now we're going to look at how we can look at this data. All right, so first things first, we're going to move our subscales over because that's what we want to do. Note that I was able to push my control key. If you're on a Mac, it's a command key, and I was able to select more than one variable at one time. So then I click over, and that puts them immediately over here, and I have the basics. Boom, done. Basics are done. But, you know, this isn't really helpful. I want to look and see at how they did differently across genders. So I'm going to click gender and I'm going to split my data. So now I have subscale A, female, male, subscale female A, subscale C. So I can see how they did as genders, right? Statistics, same thing. I can, you know, decide, you know, what other information I want. I can do box plots, correlations. I can see if there's any outliers. So this is for subscale A, subscale B, and subscale C. So I see those out, there's no outliers. I can do scatter plots, make them clean scatter plots with a linear line. And now it's going to show me, and I love the way it color codes it, right? So here I can see how the males relate to the females. The males relate to the females. Very interesting relationship here that they're almost, opposite of each other. So that would be something that would be of interest to me as a researcher, like why are the male and female so different? And so, yeah, those are some of the things that you can do to play with that. That makes sense on how to create subskills and what to do, anything?
Sure.
Okay. All right. So that is most of the descriptives. Let's take a look at some actual tests now, some inferential tests. So let's jump into t-test, which really aren't too robust for dissertation, but might be something that we're using for other research. So let's start out. I was just looking to see which data set I wanted to use. So we'll start with independent t-test. So independent t-test being two different groups of data, right? So we're comparing two groups and all we have is one score for each group. So the example that I have is actually about juries. So we're going to look at a jury data set. So it is right here, jury study. All right, so one little tip is if you open up a bunch of different data sets, JASP will open up to 8 windows at a time. So if you have more than 8, it'll stop opening. You'll be like, what's wrong? Why isn't it opening things, right? And that's why it'll only open 8 data sets. There's a function in the preferences that you can change, but a lot of times I'll open and then I'll just close the old one and, then reopen this one. Okay, so we have a jury. So we have jury 1 and we have jury 2, and then we have the amount of sentencing that they recommended for somebody who had been convicted of a crime. Now, there was a difference between jury 1 and jury 2. Jury 1 just thought everything in the trial went fine, there was no issues, and the person was found guilty and they're going to make a recommendation on sentencing. Jury 2, however, was told that the judge had withheld information, had withheld evidence during the trial that the original jury that had made the conviction did not know about. So they knew that information had been withheld. And we want to see if there's a difference in what they recommend in sentencing based off that information, right? Whether they knew or didn't know that information was withheld. Now, first things first, I have to check my levels of measurement. This is nominal, and that makes sense. In my class, my stats class, I talk about nominal being like buckets. So I have bucket 1 for jury 1, and I have bucket 2 for jury 2. The sentencing, however, is listed as ordinal, and that's not right. Sentencing is time, so that should be scaled. So I'm going to click this. In my data sets for the 734 class, I intentionally misset up some of the levels of measurement to see if students will catch that. Like that's something that I just drill into them is to make sure that level of measurement is correct. But sometimes when you bring data in, JASP makes its best guess as to what the level of measurement is, and it doesn't always know. It's not always correct. And so that is something you might have to fix. Sometimes data will come in that is numerical into JASP with this nominal symbol and an A, which means that JASP thinks it's text. And unfortunately, you can't fix it in JASP. So if you ever have that come in and you didn't mean for it to be text, it's meant to be something else, you'll actually have to go back out to the data set and you'll have to make sure that the format of the data in, say, Excel is set to number and not general, or set to number and not text. And there have been a few instances where I've actually had to recreate the data file to get it to let go of that assumption that it's text. So just some little quirks that I've learned over the time that I've been working with JASP. So we're going to do a t-test now. So we're going to go, we've set our levels of measurement. You could recode this to jury 1 or 2, but because I am calling them 1 and 2, this is fine, but I could rename these if I wanted to, the nominal. All right, so I'm going to hit t-test, and we're going to do a classical t-set. JASP does do Bayesian stats too, which is based off of a different system. Classical stats is frequentist. It's talking about counts and things and probability, and Bayesian is based off a different system. It's growing in popularity, but we're just teaching classical stats in this class for now. I might go into Bayesian in the advanced that we're developing, but haven't decided yet. All right, so our dependent variable, the outcome that we're looking at, is going to be the sentencing. So I'm going to move that over to the dependent variable. And then jury is going to be the grouping variable. And just so you both know, all of the steps that I'm doing with you right now are written out explicitly in that manual that I shared with you, like screenshots, step by step. So you'll be able to go back, link to the data file, and do this if you that's better for you to practice afterwards. That's what you want to do. So this gives me the independent sample t-test. My t is -3.3297, and the first thing that I always say to students is, okay, this is great, but the first thing you need to look at is its p-value, right? To see if it's significant. If it's less than 0.05, it's significant. If it's 0.5 or higher, it's not significant. And so this one is significant. Okay, so this is a significant t-test, so there's a significant difference. In the 734 class, I stress interpretation. I'm like, you can calculate numbers all day long, but if you don't know how to interpret it, it doesn't mean anything. So I really work with students on writing hypotheses and then writing their interpretations and making sure they know how to support their interpretations with the data, right? So for example, let me show you what that would look like. Well, let's go through the assumptions real quick first, and then I'll show you the full interpretation, because that's the second thing that I stress is assumptions. That in order to run parametric statistics, the assumptions of that statistic have to be met. So what are the assumptions for a t-test? Well, the first assumption is that the samples have to be independent of each other. All right, so in this case, I know nobody in jury 1 was also in jury 2. They were mutually exclusive, so I can check off that assumption. The next thing I have to do is see if the dependent variable, the outcome, is normally distributed across each group of the independent variable. And it's very easy to do this. I'm going to click my assumption checks for normality and equality. And so what I'm looking for is my Shapiro-Wilk. And so my Shapiro-Wilk is right here. Okay, now this is, you got to turn your heads around if you don't know this one already, that for Shapiro-Wilk, I want it to be greater than 0.05. So if it's greater than 0.05, then I have normality and it's not been violated. So that one is one of the few statistics that we want it to be higher than 0.05. So for this one, the jury 1, it was 0. They had a Shapiro-Wilks of 0.9134, and it was not less than 0.05, so that's great. So that means that the normality was not violated here, and the same thing for here. This is greater than 0.05, so the normality was not violated there. The next thing I want to do is check for skewness. To do that, I'm going to have to go to descriptive statistics. So I have my independent t-test still here, and I'm going to move my variables here. So my dependent variable goes here, and my independent variable goes here. And I'm going to click on statistics, and I'm going to check skewness and kurtosis. I can also do Shapiro-Wilk here. It's going to be the same thing. She's going to put in this report. See, boom and boom. The only thing is, here's the p-value, so it's underneath it, right? That I use. So I would interpret this whole thing right here to get the Shapiro-Wilks. For my kurtosis and my skewness, which is right here, I want those to be between +2 and a -2. If they're between +2 and a -2, I don't have skewness or kurtosis that's concerning. If it's outside of +2 and -2, the skewness and the kurtosis is concerning. Skewness being how kind of elongated the data is, and kurtosis being how high the data is or how low, right? Kurtosis like this or kurtosis like this. We want a normal bell-shaped curve. So I'm looking for those to be between +2 to -2. So we're in good shape here. This one is definitely within +2, -2. So is the kurtosis. So that looks great. So that's the second assumption. The other one I'm going to do is the box plots to see if there's any outliers. There we go. There's your box plots under customizable. Check box plot, label outlier. And it's going to be these. I see no outliers labeled, right? So I would say based on visual inspection of the box plots, there were no outliers noted. That would be my next assumption check. The last one is the homogeneity of variance, which is up here. And that's my test of equality variances, Levine's test. And I'm going to be looking at Levine's. And again, if the P is less than 0.05, the test is significant and we do not have homogeneity. This is like the Shapiro-Wilks. If it's greater than 0.05, then we do have homogeneity of variance. So this looks good. This is the homogeneity is assessed and it looks good. All right, so let's take a look at, oh, one other thing, effect size. So another thing I stress in class is that significance is great. It's mathematical. It says, yes, there's mathematically a difference. However, at the doctoral level, we want to push them past that mathematical significance. And we're also going to talk about meaningfulness or practical significance. So we really want to push them to talk about effect size, which now is really much a requirement for the JARS, the Journal Article Reporting Standards. I'm so glad they made that standard, right? So now we can expect to see effect size discussed in all articles since like 2016 or so. So that's something you want to make sure students are doing if you're working on research with them, is to think ahead. If we have a significant finding, we need to go one step further. What's the effect size of it? All right. And how are we going to do that? There's a different effect size for each statistical analysis. I give them a link to a wonderful page. It's in the manual for all of you. And that links to all the different effect sizes for all the different statistical analyses and that are most commonly used in inferential statistics. So they can just go in there and choose which one they want to use. And it also has the interpretation because there's a different interpretation for each effect size as well. So in this particular one, we will use Cohen's d. That's what we use for t-test. So we'll go back up here to our t-test and we'll click effect size. We also can do a glass delta. We can do a Hedges G, which are great as well. It really doesn't matter. But I prefer Cohen's d to keep it consistent. I have them use Cohen's d for z-test and t-test. So for Cohen's d, it's added that piece right here, and it's a negative 1.6780. The negative really doesn't matter in effect size because what we're looking at is the size of the effect, and this is a very large effect. This is very large. So we would look at that, and they would have an interpretation guide for that. So when I put all of that together, what does it look like? That's what we have here. So you can see I've explained each one of the ones I just talked about. And then we have what's called a complete interpretation. So the students are being trained on how to write these interpretations. An independent t-test was conducted to determine if there is any significant difference between two juries and their sentencing recommendations based on the knowledge the evidence was withheld by the judge. All assumptions were met. Independent variable is dichotomous and measured categorical nominal level. Dependent variable is continuous. And then you'll note I teach them how to put the data in there. The Shapiro-Wilk ended normality. It was greater than 0.05 for jury 1. I gave the statistics to support that for jury 2, for skewness and kurtosis, which were between -2 to +2. No outliers for either jury assessed by the box plots. Homogeneity of variance is assigned by Levine's test. Sentencing gave the data to support it. So really stress the importance of not only saying what it is, but giving the data to support what you're saying. So they all learn how to write these data sentences. They learn what should be subscripted. They learn what should be, superscripted, all of that. So I'm very kind of particular about the details of that to make sure that it's being done correctly. And I always stress to them, this is an error here, so I need to fix that. Should be an italics P, because a non-italics P means something else. And so really point out those little details. And sometimes I'll leave mistakes in what I'm doing and I'll say, okay, who can find the mistake in this? Because I find when they can find the mistakes, it's really sticking with them more. So that's something to talk about, to play with them about. All right, and so the null hypothesis is rejected. I make sure they don't say ever accepted. It's always failed to reject or reject. And the jurors who were informed about the withheld evidence gave significantly longer Sentencing, t-test, degrees of freedom, the t-score, then the p-value. Again, that p should be italicized. And then it was a two-tailed test because I didn't say which way it was going. And there was a large meaningful difference. This is my effect size, and say Cohen's d negative 1.6780. All right. Questions about the independent t-test?
Not so far.
You're getting a blitzkrieg of statistics today. So it's okay if you do. All right, let's do a dependent t-test. All right, let me point out one thing before we switch over. So with my independent t-test, with my ANOVAs, my data is going to be coded in this way. I'm going to have one column that indicates which bucket, the groups are in, and then I'll have the score for each individual within that group. All right, so let's take a look at a dependent t-test. So this one, we're going to be using phobias. So we're going to be looking at phobias. Phobias? Okay. That one out, don't save that, thank you. Okay, so now with phobias in a dependent t-test, we have to do our data a little different, right? So because with a dependent t-test, we're looking at the difference. So, if I gave you and Tiffany both a pre-test and a post-test, I couldn't match your scores with each other's scores. I need to make sure that, Gary's scores stay with Gary's, Tiffany's scores stay with Tiffany's, so I can show what difference happened for that individual person. So I'm going to set this up a little different. Here's that little nominal A I was telling you about when it's text. That's what it looks like. So that's text. Then I have my before score and I have my after score. Now for this difference score, I actually calculated this in Excel, but I could have created a computed column where I said subtract after from before, and it would have created that difference column for me. So I could do that here in JASP, or I could have done it in the Excel that it's attached to. So that I need the difference column as well. Okay, so now I'm going to go into JASP and I'm going to calculate some results. So let's go. T-test. And now it's called a paired sample t-test, which is the same as a dependent t-test. And in this particular one, let's go ahead and do our assumptions. So I'm going to put in, I think, yeah, that's right. So I have to put in after first and then before. Okay. And we're going to do some statistics for those. So first assumption is the dependent variable measured on a continuous ratio? Yep, that's true. So this is a continuous. The difference is going to be on a scaled continuous. Is there an independent variable that consists of categorical? Yep, they are paired, matched pairs. Yep, we got the before time and the after time. And so we're going to do some box plots. I think we did it on difference, actually. I'll show you this in a second. That's when we do the t-test, we do that. Let's do it on difference. Let's do the descriptives on difference. Okay, so we are going to come up and see if there's any outliers here for our difference. Oop, no outliers in the difference. We can do our skewness, kurtosis, our Shapiro-Wilk. If I wanted, I could do mean, median, mode. It's calculating, so it's going to give me that. So I'm going to look at the kurtosis and the skewness. They're between the +2 to -2. The Shapiro-Wilk p-value is greater than 0.05. And then I will do my normality in the other one. Yeah. So let's go up here to the paired t-test. Now, one of the advantages of JASP is in a lot of the other statistical programs, if I find that I need to run a non-parametric statistic because my assumptions have been violated, I have to go back out and run a new analysis. In JASP, I can actually run the non-parametric at the same time that I run the parametric. Or if I realize the parametric assumptions are violated, I can just click the non-parametric and boom, I have my non-parametric. So for a paired sample t-test, I can click this Wilcoxon, and this is the non-parametric equivalent of the parametric paired t-test. So it's going to give me the results for both of those when I put them up. Now, with the paired t-test, it is going to give me you see how it gives me these little boxes? Most of the time, when you are doing a paired t-test, you're going to put in the last score that you collected on them first, and then put in the first score so that when it subtracts, it's giving you most likely a positive number. And so it's easier to interpret. You can do it the other way, but it's going to come out to be negatives a lot of time, and that makes it harder to interpret. So I try and teach people to put in the variable paired one, put the last score first, and then, because usually there's improvement, right? That's what we're looking for. So this first paired t-test here, this first line is if I'm running parametric. Right? So this is the student t-test or a paired t-test. Here's my test statistic, my degrees of freedom, and then my p-value, which is significant at the 0.001 level. If this wasn't significant, I might see that my Wilcoxon was, right? And then I would interpret on the non-parametric instead of the parametric. Or if my assumptions had been violated, I would use the Wilcoxon instead of the other one. And I could just even click that one off and just show the Wilcoxon if I wanted to. So I can just click, and there it is. Okay. I can click effect size too, and it's going to add the effect size over here. So it has my effect size, and it's based off Cohen's d. So there's the effect size, very large. I can also add some descriptives and do descriptive plots here. I really like the descriptive plots in the paired because it really shows potentially graphically a difference, right? So you have what are called error bar graphs. These are error bar graphs. And so you can see the before and the after. Typically, right, always, if this line and this line do not cross, there's going to be a significant difference. Okay, so this is a good graphic representation of that. I can click my normality checks, and it's going to give me that Shapiro-Wilk. Again, here's I want this to be greater than 0.05. And then I can also, give me another one over here. Yep, that's it. Okay, so that's good for that one. If I decide, most of our students write non-directional hypotheses for quantitative research, but if it is directional, I would change here to determine what the hypothesis says. So you can change this to a one-tailed t-test. Or the opposite one-tailed t-test or two-tailed t-test. All right, so that is paired t-test. It's pretty straightforward on that one. I do teach everybody that you can write the sentences a little different. So, this is a T for difference because it's the difference, and it's hard to see, but I show them how to do that. And then this is when I write my data sentence with an exact p-value, and this is when I do it as an estimated p-value. Both are correct. So I can interpret it either way. And then error bars, and here's the interpretation. Paired t-test was conducted. If there's difference in tolerance time for being exposed to a feared object before and after imagining a safe space, no outliers by inspection of box plots. I talk about the normality, the skewness, the kurtosis. Participants reported a significantly longer tolerance time of being exposed to a feared object after imagining safe space. I give the mean and the standard deviation as compared to before imagining safe space. The imagination of safe space had a significant difference. Give the T results and a large effect. Give the Cohen's d. So clear interpretation. And I tell students that if you're going to do quantitative research, use these interpretations as templates, right? Like you don't have to recreate it. Like you can just come in and you can just fill in your data, fill in the words. You've got this template. It's a very strong interpretation, and it gives you a guide for how to write the interpretation for different tests. So really try to give them those resources. Any questions? I don't know what is wrong with my little P's not being italicized. All right. Y'all ready for ANOVAs?
Sure.
All right, let's go to an ANOVA. All right, so let me, and for the independent t-test, it's the Mann-Whitney. So you can, and again, you just check it if you need to have the non-parametric. Oh, let's do chi-square, because some students use chi-square, right? And that's a pretty common one. So we'll do chi-square first. All right, so chi-square is looking at the expected values in relation to the observed values. And so I see this used a lot in different student research. and in our research. I'm just going to try to see which vouchers. Okay, so I'm going to not save that one. We're going to open up voucher data. So in this particular study, what we're doing is we are looking at the votes for vouchers, right? For school vouchers. So for, maybe, and against. In this particular data set, we expected there to be kind of equitable votes across for, maybe, and against. And so when the votes actually came in, these were the results. You'll note that we don't have like each vote in here. Right? So for chi-square, we only need to give the total number of the votes for each category that we're looking at, which again makes it super easy. And so we are going to go to frequencies, because chi-square is a frequency, and we're going to go to multi-nominal test. So multi-nominal test. And in this particular one, we're going to put vouchers, which is our nominal, into our factor. That's how we're breaking our groups up. And we're going to put, oh, I see an error. This is ordinal. We need to fix that first. This should be scaled. Should be scaled. And then we go back out here and I take votes and I put those in my counts. All right, now I have a choice. I can do equal proportions, where I am saying I think that these would have normally been equally distributed, or I can actually assign what I expected to be the result. So let's say I expected everybody to vote for, nobody to vote against, right? I can fill that in. So I have a choice here. I can either use expected proportions and say what I thought it was, or I can just say equal proportions. Let's just see if there's a difference and it wasn't distributed equally, right? And so I have a chi-square of 20.6 with the degrees of freedom of 2 because it's n minus 1, so I had 3 categories. And then I have a significant p-value because this would be 0.000003, right? And so that's a significant p-value there. Now, interestingly enough, and I'm gonna share this link with you guys, I can do this maybe even faster than that with this chi-square calculator, which is really cool. I'm going to open it up. I'll put in the thing for you so you have it there. But if I go to the, let me go back to my data here. Okay, I need to see my data. All right, so I'm going to enter this in, and the students love playing with this. So here is like this, so I can see that data. And this is a chi-square calculator that was created by Preacher. And so you come down here, and if I'm doing one simple, like a one-way chi-square like this, I can do 23, 17, 50, and then if I would say it was expected, I can say what the expected was, or I can just put in what I think the expected was, hit calculate, boom, done. Like, I think that's even faster than JASP, right? So this one is totally acceptable. It's a very well regarded calculator. So students could use this as their calculator, and it gives them their chi-square, degrees of freedom, their p-value, which you can see it matched what was in the other one. And this is the effect size, Yates P. So boom, done. They have all the information they need to interpret the chi-square. Very simple. Right. And then again, work to interpret that chi-square. Some descriptives that I would use with chi-square, definitely distribution plots. So let's move this over here, split it here. See, saying less than 3. Let's see. What other one can I use? Oh, I've done descriptive plots with this one before. What did I do different? I don't know why it's saying 1, 1, 1. Valid, 1, 3, mean. That one has me stumped. Sorry, not trying to make y'all sick here. I'm not really sure why that one's not calculating. I don't know what I did wrong on that one. But you can do descriptive plots, I promise. They look like this when you do them. So I can do a calculation of it, the voucher and observed counts. Not really sure. I have to think about that. Sometimes I have to think on these things. So, but that's the basic chi-square. Let's look at a two-way chi-square. We can play with a little bit more with that. So let's look at gender and votes. So now we've got two variables, gender and votes. All right. So now we have gender, right? Lots of gender. We have vote, and we have each person's coded their gender and coded with their votes. So there's those. So for this one, it is male or female, and the vote is coded as yes or no. So I'm going to click on gender so we can make this clear. I'm going to change this label. I'm going to change it to male, hit enter, boom, it's already changed in my data set. 2, I'm going to change to female, boom, set, already done. Close this. I'm going to click vote. The first one is a yes. The second one is a no. And hit enter. Always forget to do that. Boom. Okay, so now when my tables come up, it's going to make way more sense than ones and twos, right? And I'm going to go to contingency table now because I have more than one independent variable. So, or more than one variable. So I'm going to do gender in the rows and gender in rows and vote in columns. And it's already calculated, right? It's already giving me my chi-square. It's not significant because that's greater than 0.05, but it breaks it down contingency table wise. Okay, I can create more information. I can do contingency coefficients. With the cells, I can add my expected count. So expected count, this is what was expected. I can also add percentages, which is really important when you're doing the two sample chi-square. So you can see what the percentage was in each one of them. So this is a really helpful information for interpreting the results because then you can describe how many males were yes, how many males were no, how many males total out of the total set, how many females total. So it really helps you really give a very rich discussion of the results. So that is an example of that. I'm trying to think if there's anything else. Oh, the effect size. Which is by our Kramers. So I'm trying to remember. Oh, they're right here. By and Kramers right here. So then you can get these to interpret. What was I going to say? One thing about chi-square is if a student or if you're using chi-square for any research, you have to have a minimum of 5 in each cell. So that's really important. So if you have less than 5, chi-square won't work. So you've got to have a count of at least 5 in each one of the cells for it to work. That's chi-square. And again, you can use that here as well. So I could punch in that data into the, let's go back to descriptives because then it'll tell me the counts. So in this, I had males 37. I had 20 for no. For condition, actually, let's do it this way. The condition would be the yes or no. The groups would be the males and females. So I could do 32 and 31 here. I hit calculate, same thing. It calculates the chi-square and gives us that information. The difference is that this calculator doesn't give me the rest of the contingency table, so I don't have the percentages, which is why you would want to use JASP, because you would get the percentages in each of the groups, so you could give a richer discussion of the findings. So those were both chi-squares. Questions? Okay. Great. Let's move on to ANOVAs, which is one of my favorites. Multiple regression is my favorite, but I love ANOVAs too. ANOVAs are cool. All right, so, oh, and this is a good one. I love this data set. So let's play with this data set. All right, we're going to talk about noodles. Hopefully nobody gets hungry. So we're going to be talking about noodles. And I really like this data set because there was a survey error that's in the sampling. So that helps students understand the importance of why they have to really set up their surveys in a very intentional way and really think about how they're setting it up, because it can really impact their interpretation of it. So it's one of the reasons I really like this particular sample, because in this one, the survey was measuring how pleasant somebody finds a noodle. Thick noodle, a medium noodle, and a thin noodle, right? So how pleasant do you feel it? But when they set it up, they made 1 the most pleasant and 5 the least pleasant. And that is opposite of how we normally think, right? And so it really demonstrates how hard it can be to interpret if you don't set up your survey correctly. So this is what we'll be looking at now. So we're going to do an ANOVA. We should probably organize this so that we can determine which is which. Hold on, I'm gonna have to look to see so I can remember which one is which. I think it's thick. Okay, didn't say in here. Okay, so I'm pretty sure this first one is thick. So let's do this. Thick, medium, and thin. All right. And then, of course, we have the Likert for the pleasantness. So Likert is technically ordinal. But in this case, they are treating it as scaled, which is important for the, oh, I totally lost. Why did you go to that? Thickness is nominal. There we go. And this one is going to be treated as scale. That is a common research error, that the Likert scales are treated as ordinal. So when you have a student who is using a Likert scale and they want to use parametric statistics like ANOVAs or multiple regression, you have to ask them, what is the outcome of the scale, right? Is it the mean of the Likerts? Is it a total of the Likert scores? Is it the median of the Likert scores? The median of the Likert scores is the best way to interpret the ordinal data, but it's not typically, that's not how it's done. I see usually with Likert's instruments, they're either totaled up and become a total scaled score, or they are the mean of the scores, and that's what they use. So you just have to be very clear with the students about what's the outcome in the scoring, and not, it's amazing to me how many students I work with in dissertation who are just like, oh, I was just going to add them up. I was like, what did the developers of the assessment say to do, right? What's the scoring interpretation? And, sometimes students have to change what they're using because they weren't paying attention to the scoring interpretation guidelines for that assessment. So we need to make sure they're being true to those guidelines and interpreting and using an appropriate statistical analysis for whatever scale of data they have. All right, so we'll go to ANOVA, go to a classic ANOVA. So in this one, the thickness is my fixed factor and the pleasantness is my dependent factor. All right, so in this one, we can see that thickness did have a significant impact on what people thought about the pleasantness of it, right? This is significant with the F score. If we move from T to F, so this is the F score, and this is a significant finding. But the problem with ANOVAs is ANOVA only tells us if there's a difference. It doesn't tell us where the difference is. So we're going to have to do more work to figure out where the difference is. Because it's also a significant finding, I want to know about the effect size of it. So I'm going to click a few things so we can get some more data. Descriptive statistics, the estimates of the effect size. Since I only have one variable, I'm going to use what's called eta square. If I had a factorial ANOVA, I would also want the partial square and probably the Wilks. Here's my model. It's looking at thickness. This is called the model right here. It's looking at thickness. I'm going to do my assumption checks. I'm going to check for homogeneity. I'm going to do my QQ plots. If there's anything under contrast. No, nothing under contrast. I can restrict the order in which things are entered into the hypothesis, but we only have one variable, so we don't need that. And then we're going to check post hoc tests. So I do want my post hoc test because I had a significant finding. I need to do what's called post hoc test. And I can do any of these really, but I like to, show that really there's not much difference between them. They're just different formats, but these are the two that most students use. And then I could add descriptive plots. I could display error bars if I wanted to. I could do marginal means. There's the place where I can do non-parametrics, like the Crooks-Wallace test. So those are some things that I can click and check to look at. So let's see what we have. So here we have the model or the ANOVA table. This is my test statistic, my p-value, my effect size. I can look at the medium, thick, and thin, and this is the mean score for the medium noodles, the mean score for the thick noodles, and the mean score for the thin noodles. Now, because that survey was set up in a weird way, I know that the lower the number, the lower the mean, the more pleasant people found it. The higher the score, the less pleasant it was. So I have to remember that as I'm interpreting this data. I look at these error bars and I can tell you right off the bat from, doing this a lot, that there's no significant difference between thick and medium because they overlap. Their error bars overlap. So I know right off the bat, just looking at this picture, that there's going to be no significant difference between those two. However, the thin noodles does not overlap with the medium or the thick. So I'm going to anticipate in my post hoc that the thin is going to have a significant difference between these two. So when I scroll down, let's go ahead and look at post hoc, make it bigger. So this is my post hoc. So thick to medium, it's got a mean difference of negative 0.15. However, it is not significant. Here's the p-values for the Bonafroni and the Tukey. When I look at thick to thin, when this is a space, it just means drop that one down. So thick to thin, there is a significant difference here. So that's significant. And for medium to thin, there's a significant. So I would report those out as being significant. So the thin noodle was significantly more pleasant for the consumers than the thick or the medium. I can see I've got a good linear grouping here of my data. It's very tight along the line of regression here. So that QQ plot is showing there's linearity. Oh, I can't talk. And my assumptions check, my Levines is greater than 0.05. So that shows that I have normality in my data set. So that's all good. That's cool stuff. You can interpret this. It's awesome. So let me scroll down and then you can see all the data that we can get from this. This is a full description of the results. So you can get a ton of information just on that one little data set and comparing the three noodles. But I think it is a very important lesson for students to see that reverse interpretation and to make sure that they understand that the way you set up your survey can be very impactful on how you can analyze it. I will also say that I use this as an opportunity to talk to students about the importance of when you create your own surveys or instruments to try to ask for information in as broad a scope as you can using your levels of measurement. So when possible, instead of asking for grouping of information, I encourage students to collect data on a scaled version because you can always change a scaled to a nominal or scaled even to an ordinal, but you can't change the nominal to a scaled or, even the ordinal easily to a scale. So I always say if you're creating your own instruments, if you're creating your own research instruments, try to collect a scaled number first, and then you can group it if you want to into nominal groups. So like age, right? Get the specific person's age. And then if you want to group your data, to say people who are between 50 to 55, 56 to 60, you can group it, but you can't ungroup it when you have anonymous data. So I always stress that lesson, like that's a hard lesson to learn because once you collect your data, unless you want to go back and recollect your data, you can't ungroup it. So it's important to think about those things as you're going through. Okay. All right. So any questions about the ANOVA and how to do that one? Great. Let me think about which one to show you. because we don't need to do anything by hand. Factorial, maybe, factorial ANOVA, and then we'll do an ANCOVA. So factorial ANOVA, I'm trying to think which data set I want to use. Oh, let's use weight loss. Okay, so we're going to use weight loss. Weight loss. Okay. All right, so in this data set, I have a treatment for weight loss, I have gender, and I have the amount of weight that they lost. So if I remember, it's low, high. Yep, low, high. So this is going to be, I'm going to click on this, and I'm going to make this one low impact. And this is going to be high impact. So these individuals participated in a low impact exercise treatment, and then the other ones participated in high impact. And then for gender, here, click, thank you. Did it change? Yeah, okay. Gender, there we go, gender, male, and then female. So enter. Now I want to show you what this looks like. I always ask students to draw out their ANOVAs because I think it helps them visualize things better. So we always create a chart. So always have them create this chart. This is really helpful if you're like supervising research or dissertations, to ask them to draw it out so they can visually see what the data is doing. What are you doing here? So with a factorial ANOVA, what's really powerful about a factorial ANOVA is that we can get main effects. So I can look at differences in the male and females, right, between them, and I can look at differences between the low and high. That's my two main effects. But I also have the power to look at the interaction effect of male with a low impact to male with a high impact, with female low impact, female high impact. So I'm looking at the interaction of those variables too. That's what's powerful about a factorial ANOVA. So I always have them draw out a chart and fill it in, and then I have them identify what their independent variables are, or factors as they're called in ANOVAs, and their dependent variable. And then I have them state their hypotheses. So if I have two independent variables and one dependent variable, I'm going to have three hypotheses. I'm going to have a main effect one, a main effect two, and an interaction effect. So for this one, there's no difference in weight loss by exercise impact type, low or high. That's my first main effect, right? It's looking at the type of treatment. My second one is there's no difference in weight loss by gender, male or female. That's the main effect for gender. My interaction effect is going to be there is no difference in weight loss by exercise impact, low or high, and gender, male or female. Okay, so we're going to have three hypotheses. If they have, three variables and one dependent variable, they're going to have four hypotheses, so you've got to have a main effect for each independent variable, and then you have to have an interaction effect for all the variables. Okay, so the difference between an ANOVA is just going to have one independent variable and one dependent variable, but it's going to be across three groups. So once you get out of two scores, you move from t-test, T for two, to ANOVA, which is three groups or more. ANOVA's one independent variable across three or more groups or buckets. And factorial ANOVA is going to have two or more independent variables and one dependent variable. A MANOVA is going to have one or more independent variable and more than one dependent variable. So that's when we switch to a MANOVA, is when they have more than one dependent variable. And I actually have a chart. I think, where is it at? Oh, right here. I have a chart on page 106 that explains when to use what. So the number of independent variables and the number of dependent variables. So it's explained here. Okay. All right, so let's go back and let's look at this weight loss. So we are going to look at weight loss. Let me scroll down. So there we go. Okay, so we're going to test our assumptions, make sure that all of the assumptions are done. So let's go ahead and start doing the calculation. So we'll go to ANOVA. This isn't a repeated measures. They weren't measured more than once, so it's just an ANOVA. And And our dependent variable is the loss, the weight loss, and our fixed factors, I'm going to hit my control key or command if I'm on a Mac, and I'm going to move those over to the fixed factors. Now, it's giving me an ANOVA source table, and so I have results for treatment, so that's the high or low impact. So here's my F score, it is not significant. The gender, I have my F score, it is not significant. So treatment, the type of exercise they were doing, not significant. Gender, not significant. However, the interaction effect, which is what this one represents, is. So when I combine the two and I consider their impact together, there is an interaction effect. But just like a regular ANOVA, one-way ANOVA, I don't know where the difference is. Was it between the males with low impact and the males with high impact, or the females with low impact or the females with high impact? I don't know where that difference is. So I've got to dig deeper to understand that. So I'm going to click a few things so I can get some more data. I'm going to click my descriptive statistics. I'm going to click my effect size. The model's already set up. And because I know now that these two aren't significant, I could take these out and just have this. So it's cleaner. So if I wanted that for, say, my dissertation, you know, I could do that, but it's, you know, we don't want to do that. So, let's see, need you both back over here, please. Thank you. All right. And then assumption checks. I'm going to check my homogeneity. If I needed to run some additional tests, I could here. I'm going to do my QQ plots. I don't need contrast. I'm going to run my post hoc. I'm going to run post hoc on just this one. Why? Because that was the only significant finding, right? These two weren't significant, so I don't need to run post hocs on those. I just run post hocs on the actual interaction. I can do, this is kind of cool. You can flag the significant comparison. So in the pairwise comparison for the post hoc, you can flag it. I could do descriptive plots if I wanted to. So this will show me, this is kind of overwritten each other, but it will show me, if I copied it, I could adjust this so that it wasn't overwriting. So I can get my descriptives. I have my equality of variance, my Levines, that is met. I have great linear grouping on my data. And then I come down here to my post hoc. So with the post hoc, I can see that low impact males and high impact males, not significant, not significant, not significant, not significant. Oh, and see these little asterisks? That means that if it's a single asterisk in JASP, it means it's significant at the 0.05. If it's a double asterisk in JASP, it's a significant at the 0.01. If it's a triple asterisk, it's significant at the 0.0001. So you can see these two are significant. So none of these are. So I would report that high impact males had and high impact females had a significant difference in weight loss, and low impact females and high impact females had a significant difference in weight loss. So I've interpreted it even further. And then I should have a eta square appear. Here's my eta square, and I can interpret that. An eta square is anything over 0.15, I believe, is significant or is very large. So these are probably medium effects, and this is a large effect. But these wouldn't be interpreted because they had insignificant or non-significant results. The only one I would interpret is this one, which is a large effect because it's over 0.15. So lots of information, right? You can get a ton of information here about this ANOVA, and you can find out exactly where those results are and what was significant about it. And yeah, I'm trying to think if there's anything else. That's all I can think of for this one. And when you do the interpretation for this one, it's a bit longer, but you know, it says factorial ANOVA was conducted. It talks about each one of the assumptions and how they were met, gives the data to support it. And then it talks about the significant difference between each one of them. And then where there were not significant differences, all right. And again, those etas would only be, the effect size is only interpreted for the significant findings. And then I do a mean description of the differences in the people and what they lost. And then I can also depict that in a descriptive plot. Okay. So that's a factorial ANOVA. We'll do one more, well, two more. We got ANCOVA and then multiple regression. And then I'll see if there's anything else y'all want to know. So let's do an ANCOVA. ANCOVAs are fun. I find a lot of research that students are doing, even faculty are doing, would benefit from an ANCOVA, but a lot of people don't think about it, right? So, especially in the social sciences, oftentimes there are confounds that we may not be able to capture or that we may know exist, and we try to measure it as best we can, but that is going to affect the outcome. So, one of the dissertations I'm working on right now is someone who's looking at burnout in clergy, right? And is looking at, does burnout in clergy affect their referral rates to counselors for their, parishioners? Now, one of the things that we came up with in talking about that is, okay, what could affect the referral rate? Well, a lot of clergy have training as counselors, but not all clergy have training as counselors. And so the thought was that if somebody had a certain amount of training as a counselor, they'd probably be more likely to refer to other counselors, right? So we established the covariant as being the pre-existing training as a counselor. So that's the covariant. So we're going to control for that difference. So if somebody has pre-existing counseling training, that's going to be adjusted so that we can compare the results, because we can't really compare those referral rates if we don't account for that pre-existing, probably predisposition to referring. So that's what we're going to be doing. I wanted to show you guys, it's kind of a funny subset, but in the JASP database, they actually have a data library. You can also connect to the Open Science Framework if you have an account and get tons of data through that to play with. But the data library is one that's actually built into JASP, and it has tons of like data that you can play with. One of the things that we're going to play with, though, is ANOVA. And some of these are funny. They're from Andy Field. He's in England. He's a really good statistics professor. I like Andy's stuff a lot, but he sometimes uses off-color examples to help students remember, because the English have a different humor than we do over here. So so like this data set is Viagra. So this is really talking about the effects of Viagra, and what they're saying is that the partner's libido is going to be impacted by the partner's libido as well as the dose of Viagra. So this is looking at dose of Viagra, the person's libido, and the other person's libido. But I'm going to show you kind of why it matters. I'm trying to figure out what these numbers are so that I can Yes, we know that. I can't remember what these are. Oh, here we go. All right, so number one is placebo. So they actually didn't get anything. Number two is low dose. Number three is high dose. And then the libidos are scaled. So we will just say scale and scale. So it's a rating. They're rating themselves. So it really should be ordinal, but we're going to treat it as Likert. All right. So we're going to go into ANOVA, and we're going to do an ANCOVA. Here's our ANCOVA. And we're going to say our dependent variable is the libido. Our fixed factor is going to be dose. And I just want to look at this one first. So we have the ANCOVA, and we're looking at the results for dose, which is our outcome. And so here you can see there's no significant finding, right? None. It's not significant. What happens when I add in the partner covariant, though? Now I'm accounting for this as a covariant, and now I have a significant finding. When I control for the partner's libido and account for that as well, that means that there is potential effect of the dose to, impact the libido of this couple. And so again, I can do descriptive statistics, I can do effect size, the model's already created, I can check my assumptions. I can also do post hoc if I wanted to. And then I'm trying to look, where are marginal means? So I'm going to do marginal means. Okay, so the descriptive statistics. This is before I account for the covariant. So before I account for the covariant, the high dose had a mean of 4.84, the low had a dose of 4.87, and the placebo had 3.222. Okay, that's before I accounted for the partner's libido. With the marginal means, that has adjusted those mean scores now using the covariant. So these are, when I account for the partner's libido, this is what we really saw with the effects of with the Viagra. So I think it's a powerful tool to show that accounting for the covariant is really important. Like there are things that are impacting the research we're doing that we have to account for so that we can see the real effect of what we're studying. Right. And that's the power of an ANCOVA, is it allows us to do that. And so if I had more than one dependent variable here, maybe I was measuring their relationship satisfaction as well, then I would use a MANCOVA, because a MANOVA is for more than one dependent variable, right? But I can do a MANCOVA as well and just have the two dependent variables. And the MANOVAs are run in the same place. They're right here. MANOVAs, and you just have more than one dependent variable that you're accounting for. And the power of the MANOVA is that it accounts for not only potential interaction between the independent variables and the dependent variable, but it's also now accounting for interactions between the multiple dependent variables. So you interpret all of that. You interpret the independent variable to the dependent variable, and then the dependent variables and the dependent variables and how they impact each other. So that's a quick run through. And a repeated measures ANOVA is simply when you have, it's like a paired ANOVA, right? When we have more than one score. So sometimes one of the other dissertations that I've helped with recently was looking at some of the neuroscience technology. And so there were 3 groups. And one group got just regular talk therapy. One group got like very low stimulation through electromagnetic stimulation, and then one got a more intense electronic stimulation. And the person that was doing the research did an initial measure. I think it was it was either focus or depression, I can't remember, and did the initial evaluation. So he collected a pre and he collected the post. And originally he was looking at comparing those pre and post across the 3 groups. And he came to me and he's like, I didn't get anything significant. And I'm really surprised by that, right? I'm like really surprised that I didn't find any significant findings. So I said, well, let's take a look at the data a little bit deeper. So the first thing I had him do was run outliers, right? Like, let's look at your box plots. And sure enough, there were about 5 or 6 outliers in the group. So I said, your power is not going to get that significantly impacted by removing those. I think that you might want to at least run it without those outliers and see what the results are. So we copied the data set, we set up a new data set because we didn't want to lose the original data set, and then removed those outliers and ran the data again. Still came up no significant difference. I said, I'm looking at your groups using this error bars, right? Looking at the error bars right here. Where did they go? Hiding. I don't know why they didn't come up. Oh, because I didn't put anything in here. That's why. There we go. So the error bars. So in his case, his control error bar was like up here on his pretest, and his the low and the high, were down here. Like I could see there was like no overlap between the control group and these other 2 where he had done his treatment. And I was like, that's a problem, right? I said, that's telling me that there's something already at play before you even did your treatment. Right? Something is causing this difference between these groups. So I said, let's run it as an ANCOVA without the outliers. And bam, we had a significant result when he used the pretest as a covariant instead of using it as a comparison. And he used it as a covariant to say, this is the pre-existing baseline. And then we are going to account for the difference that already existed at the beginning. We're going to do our treatment. We're going to be better able to isolate the effects of that treatment. So it's this is one of the things I like about JASP because I can play with it, right? I can say, hey, show me your error bars, show me your box plot, show me this, because then I can see where there might be problems that a student may not be yet ready to think beyond. I'm just doing the steps that Dr. Stretch told me to do, right? I want them to think creatively and critically about it as they're looking at their research. All right, any questions about ANCOVAs and MANOVAs, repeated measures ANOVAs? Okay. All right, last one is a multiple regression. Let me see which data set I want to use for multiple regression. So let's go back to our data sets. Oh, they've got me in the other one. Let's see, curriculum. Okay, let's see which. Oh, let's do. I think exam revision would be good. Let's see. Yes, perfect. Okay, so check my data, right? So this is going to be a test score, the number of hours somebody studied, their anxiety rating, and then I'm going to give age is going to be scaled. Okay, so I want to see if the number of hours somebody studies, their anxiety, or their age impacts their final grade in the class. Okay, so that's what I'm trying to do. So this is multiple regression. So with multiple regression, I'm going to go first, I'm going to run a correlation. So I'm going to take all of my variables. Again, I'm holding down that control key or command key, and I'm going to put them in here. Because all of my variables are scaled, I'm going to use Pearson R, which is the most common. I'm going to flag my significant correlations so that I can see it more clearly. Now I have my correlation matrix. All right, now the first thing I'm going to do in multiple regression is I've got to determine if my independent variables are correlated with my dependent variable. Because if an independent variable or predictor variable is not correlated with the dependent or predicted variable, it can't predict, right? You got to have a relationship to predict. So my predicted variable or my dependent variable is the score. So I'm going to look down this score line, and I can see that hours of study is significantly correlated with score. Anxiety is not correlated with the score. Interesting. Age is correlated with the score. Okay. Now, if I were just doing multiple regression as a researcher, I would go ahead and throw out anxiety because it doesn't have any relationship with score. So I know it can't predict that, but I'm going to leave it in just to show you what happens when you run it with the multiple regression. Okay. Now, the second thing I have to do with my correlation matrix is I have to see if my independent variables and my independent variables and my independent variables, if they are correlated. If they are highly correlated with each other, it's actually going to cause an overlap. And so when I create my prediction equation, I'm going to be accounting for part of that multiple times, right? There's going to be this part that's overlapped, and it's going to overestimate my prediction. So I want my independent variables to be as little related to each other as possible. Okay, so a non-significant finding on this correlation would be great because then they're not related to each other. So let's look at hours of study to anxiety. So here's hours to anxiety. They are not significantly correlated. So if this had been somewhat correlated, I could have kept it in. Age. These are significantly correlated with each other. So they have a correlation coefficient of 0.7318. And if I multiply that by itself, it tells me that hours of study and age account for 53.5% of the variance. So I can square this and find out what the variance is. So 53.5% of the variance is accounted for in this relationship. All right, that's a pretty big correlation. So I'm kind of like, I don't know if this model is going to be very strong. If I keep them both in there, I'm going to probably over predict somebody's score, right? So as a researcher, I probably want to choose one or the other to keep in there. We're just going to keep them in for now to see what happens, okay? And see which one is the best. And then the same thing for age and anxiety, not correlated. So if anxiety had been correlated with score, it would have been good to keep in. Okay, but it wasn't correlated with the score, so it's probably not a good thing to keep in, but we're gonna just keep it in so we can show you what happens. Again, you can see these 3 asterisks means that they're significant at the 0.0001 level, right? So good way to interpret. It helps you catch those interpretations really quick. All right, regression. We're going to go to linear regression, and our dependent variable is score, and then our covariants are these guys, and we're going to put them in, and it's going to give us this beautiful model right away. I don't interpret this first. That's just kind of like a baseline. Like, so nothing happens with this first line. I only interpret the second line. And so for the second line, what it's telling me is that 83.4% of the variance in score is accounted for by the things that I threw into this model that are significant. So let's see what's significant. I'm going to close this up a little bit so we can see this a little better. All right, so here's my model summary. So that's for this line right here. Okay, so I just interpreted the adjusted R. You can interpret R square or adjusted R square for the variance. I choose to use adjusted R square because it accounts for the number of significant variables in the model. So it's accounting for the number of variables. This one does not account for the number of variables in the model. So this is more accurate, but both are correct to use. You can use both. So this is the total model. There's their F score, 32.81. It is a significant model, so it's telling me yes, what some of these things are accounting for a change in the score. Okay, then I go down here. This is my intercept or constant, which would make up part of my prediction equation. It's the baseline. And then I go to hours. Hours, this is the coefficient for hours. I'll show you what that means in a second. And then this is the t-score for that. And here is the p-value. It is significant. So hours significantly contributes or has a relationship with score. Anxiety does not. I'm not surprised by that, right? Because in my correlation up here, they weren't related to each other. They're not correlated here. So this matches that. That makes sense. And age is significantly correlated. Because this is not correlated, I would want to go back in and I would take this guy out. Boom, he's gone. All right, this is called stepwise, backwards stepwise regression now, because I'm taking things out that have the least amount of explanation for my model. My model has gotten a little bit tighter. Now I feel like it's getting closer. My F-score went up. My p-value is significant, so I'm getting a much better model now than I did when I had anxiety in there muddling up things. Again, still significant. Hours are significant and age is significant. But in the back of my head as a researcher, I'm going, but these two guys were so correlated with each other. Honestly, I'd probably choose one over the other. And so this one is has a stronger significance. I would probably throw out hours and keep age. Okay, but we're just going to play with it. And so I can show you what it would look like if you put it into a prediction equation. So let me find that prediction equation so I can show you what that would look like. Prediction equations are what make multiple regressions so unbelievably cool, because you can tell the future, which is fun. All right, so nope, I want to keep going. That was the wrong one. Let's see, where is it? There's a lot of assumptions to check with multiple regression too. We can go through some of those if you're interested, but I wanted to show you the prediction because that's the fun part. Where is it at? Okay, here it is. All right, so I'm going to try to make it so you can see both pages. Oh, no. All right, so in this, you can see over here, we have, this was based off the other one. Let me go back and put this guy back in. Okay, normally I wouldn't keep him, but we're going to keep him in there so we can match to what I have in here. Okay, so we have these correlation coefficients. So here you can see that this is the prediction equation. So you have your y predicted. This is what I'm trying to predict. This is the first variable times its raw score, second variable, blah, blah, blah. I have it explained up here. And then this is the constant or the intercept. So that's the negative 11.823. And then I take the coefficient of the first significant variable and I put that in. And the second significant correlation or coefficient is the age. I did not put anxiety in here because it's not significant. It's not significant, so I don't put it in there. So I have students solve 25 for anxiety score 63, studied 40 hours. The anxiety score is out because it wasn't significant, so I can't calculate for that. So then I punch in the 40 hours times its coefficient for hours, and then I type in 25 for age, add the subtract the constant, and I solve. And I would predict, hopefully this is a 60-point test, that the person would earn a 59.94. So I've taken data I collected on other students, right? And now I've created an equation that I can predict how future students will do on this using this prediction equation. And as I get more and more data, I can add that data and recalculate the prediction equation and get it tighter and tighter and tighter, because the larger you get, the closer approximation you have of your population, so the more accurate the prediction equation would be. So that is an example of multiple regression, which is another very common popular tool that students use in their dissertations. And in this document, I have explained step by step how to interpret all of the assumptions. I was just going to get you to the list of assumptions. It's too far down. Yeah. That's the little quiz. There we go. Linear regression. I went too far. Those are, I want to show you the multiple regression ones. Where are they? Oh, here they are. So here are the multiple regression assumptions. So in every one of the statistical analyses, I have a list of assumptions listed of what assumptions have to be met. So if you have a student or you're doing research yourself and you're using a quantitative analysis, all the assumptions are listed for all the major statistical analyses. And then it goes through how do you test for those assumptions? And it gives you an explanation as you go through each one of the assumptions and how do you interpret that assumption. So you can use this with students so that if they're doing a proposal, if they say they're going to do quantitative research and they're using a statistical analysis, that's the first step. Like they shouldn't be just running the statistical analysis. They have to show all those assumptions before they move into the analyses. And then depending on the analysis, if it's significant, there's going to be an effect size that they have to do. So it's assumptions, test statistic, effect size, and if appropriate, post hoc analysis to determine where the differences are. So those are the steps that they should be following in order to do any quantitative research. So thoughts, questions?